Let's have a look at this very simple two-player normal form game. The two players each have two possible actions or strategies that they can use. They could either play heads or they can play tails. This is called the matching pennies game. So if you want, you can think of it as they each have a penny and they have to put it on the table and they put their pennies down simultaneously. If the pennies match, they both have heads, then player one wins and player two loses. So player one gets a payoff of one, player two gets a payoff of -1. Similarly, if they match and they're both tails, player one wins. But if they don't match, then player two wins. Player two gets a payoff of one, player one gets a payoff of -1. So in this very simple game, if we wanted to understand what's happening, we would really need to understand, we would have to do an analysis from both the perspective of player one and the perspective of player two. So let's look at player one. Should player one play heads or should player one play tails? Well, if we contemplate playing heads, then whether you get a payoff of one or payoff of -1 depends on what player two is going to do. So without having some sense of what player two is going to do, it's not possible for us to tell whether heads is a better idea or tails is a better idea for player one. Because if if one were to think two is going to play heads, then also playing heads is better than playing tails. On the other hand, if player one thinks player two is going to play tails, then playing tails is better than playing heads. So in order to figure out what player one ought to do, or what he would do, we need we need to formalize this idea of what player one thinks player two is going to do. So what does player I think player J will do? That's what we call a belief. Since we want to treat this in a formal mathematical way, we're going to use the notion of a probability distribution to describe player I's beliefs over what the other players are going to do. So I's belief will be a probability distribution over the strategies of other players. In this example, player two has two possible strategies. So here, player one's belief is a probability distribution over player two's strategies, which are either H is a set H and T. Now, probability distribution over a set of two things is described entirely by a number P between 0 and 1 would be the probability of H, and 1 minus P would be the probability of T. In general, beliefs over what player J is going to do are a probability distribution over the set Sj, and will represent the set of all probability distributions over the set Sj by delta of Sj. So this is the all probability distributions over Sj. And it will represent an element of this set, theta j, as theta j are beliefs about what player j will do. So these theta j's are such that for all strategies Sj in the probability has to be greater than or equal to 0. And if we take the sum over all Sj, so look at all the strategies, then the total probability that one of the strategies is played has to equal 1. So any such function is a probability distribution over Sj. So any such theta j, which maps Sj to real numbers, is a probability distribution over Sj, i.e. a belief over what J will do.
Going back to our earlier example here with the two strategies, I just want to point out a couple of salient points. If P equals 0, then player 1 thinks 2 will play tails for sure. If P equals 1, 2 will play heads for sure.
For these two special cases, it's clear how you would calculate the payoff of player 1 from playing either heads or tails. So if he thinks player 2 is going to play heads for sure, then his payoff from playing heads is 1, payoff from playing tails is -1. And similarly, if he thinks player 2 is going to play tails. But what do we do if his belief is that player 2 is going to play heads with some positive probability and tails with some positive probability? Then in order to calculate the payoff of player 1, we're going to need the notion of an expectation. So we're going to calculate the expected payoff. So if player 1 has belief about player J's actions as theta j, then we'll write down his utility or his payoff from choosing the action or the strategy Si, given his beliefs of theta j over what j is going to do, as follows. For each possible strategy that player j could follow, we look at the utility or the payoff that player I would get playing Si when player j plays Sj, and we multiply that by the probability that j is going to play Sj. So this is the expected value of the payoff of player I when he plays Si, and the random variable is Sj. So how would this change if there were more than two players? So if I was facing more than one opponent, then here, instead of just his belief over what J is going to do, but rather what everybody else would do, and his expectation, so his expected utility, would not just be over what J does, but rather what everybody else would do. So we sum over all possible strategy profiles for everybody but I. We look at the utility that player I gets when he plays Si and everybody else plays S minus I. And we multiply that by the probability that everybody else plays S minus I according to I's beliefs. And we sum that over all possible S minus I, so all the other things that others can do.